Hello and welcome to this next session in our Julia and Agents.jl tutorial. We're now in the code editor in Visual Studio Code, and I have just opened a folder called ABM tutorial, and the folder is empty, and I've created a new file in which to write all my code. And we're now going to apply the concepts that we learned in the last video to set up our first agent-based model that is in the realm of epidemiology and trying to understand how a disease may spread between agents. And for that, we'll do the first thing, as always. We'll open our Julia console. And in the Julia console, by the way, things that you should see is that I'm here in the Julia environment version 1.9. And one thing we want to make sure is that we're in a local environment. So I go into closing bracket. You don't see that I'm typing it because it immediately switches into the package manager mode, and I'll activate this folder. And now you should see that I'm in ABM tutorial package, and I can add agents. And by adding the agents package, I will have Agents.jl available, and this will take a moment, so I will give you the benefit of zooming forward in time and not having to watch how this installs on my machine. So take some time and relax while it is installing. Okay, we're back. We have 26 dependencies successfully pre-compiled in 68 seconds, and I already had 75 pre-compiled on this machine because obviously I've been using Agents.jl. We can quickly go up in our history and see what happened. Okay, we, in theory, array tools and quick heaps, we could have do a version, but there are dependencies that prevent it from going higher. But that's so much for installing dependencies at the moment. So what we'll do now is we'll create a main.jl file. Let's save this as main.jl, which is our core program that we will want to use. And the first thing we always should be doing is we should use the pkg package manager and tell it to activate our local folder. So once we execute this, we're always in the environment that we want. We see that Julia is down here still, so VS Code still assumes we're on the version 1.9 Julia, and to prevent it from recognizing this and going into the actual environment, we can quickly close it by doing on the Macintosh Option JK for Julia close and JO for opening it up. And now we should see that we're in the, right package. I'm not sure why this is showing as, yeah, I can pick, is this the ABM tutorial Julia workspace? No, this is it, yeah. Okay, I'm activating this environment, so it is also clear to the to Visual Studio Code that we're working in this ABM tutorial, and it takes note of this in a .vscode folder which contains a settings.json, which just basically says this is my Julia environment path. And okay, we can ignore this from now. And what are we trying to do? I told you we need three things for a simulation. We need an agent, we need an environment, and we need behavior, which is kind of like rules for the agents, or we can call this steps, since we're in discrete time simulation. And the first thing that we should think about is in which environment do we want to put our agents. So let's move the environment up and the agent on the second slot, and the third would be our behavior. So what will we do as an environment? We want to keep it simple in the beginning. So the idea that I have is that we will have a grid-based agent space. And so we would probably do something like space equals, we can do a grid space single. So the grid space single is basically a lattice, and I need to tell it the dimensions. And if I do it like this, and I think periodic equals false, this will give me a Grid space single is not defined. Oh, obviously it's not defined because we did not activate the agents.jl package. And interestingly, it shows me a preview if I'm hovering it, which is a little broken, but agents.jl is now pre-compiling and it's now available, and now I should be able to do a grid space. What does it say? Grid space single, and it says I need a tuple. Oh yeah, obviously the grid space single does not only require the dimensions. By the way, if you're coming across an error, it's really helpful to look where the error first occurred. So this one was the previous error where we didn't have agents.jl loaded, and this is the last error. And you can try to read it from the back to the front, but it's helpful to go to the front because that's where you get the most descriptive error message. And it says no method matching grid space single integer and periodic bool. Why does he say this? Because that's how we've called grid space single. We gave it an int64. It assumes that the number 2 is a int64, and periodic is a boolean, and that's why it says this is the signature. That's how we call this. That was used. It tells us the closest candidates are tuple var arg int64d periodic metric, and this is hard to understand. But let me quickly unravel this. So the idea is it requires a tuple, and then it can get periodic and metric, and the tuple requires a variable argument of int64 and d. So what this actually means is we need a tuple, and there are multiple ways of having tuples. So this could be the most simple tuple would, I don't even know, is this a tuple? Let's check if this is a tuple. No, this is just an integer. So the smallest tuple that we can have is something like this. This will create a small tuple. So let's do it like this, and the arguments to that tuple can be any amount of int64s. So this is a legal grid space, and it will give you feedback. What we're using as a metric is the Chebyshev neighborhood, and periodic is false because we set that to false. But we can also go, I think, this way, and now we have a 3-dimensional metric, but let's not go in that direction. That's kind of hard to understand. So let's say we have a grid space single, and we'll do it 20 by 20, and this is the smallest possible grid space. We can move smaller, but we have now a 20 by 20 lattice where on every node we can only have one agent. And since we're on a lattice, we should also have an agent, and we are using the agent macro. We're giving it a name, and I think for a good name we can either say person, and yeah, let's say person, and the person should inherit from the grid agent, and it should inherit from the grid agent 2 because we have 2 dimensions, and we go begin and end. Oh, it automatically filled in the end, and if I do that, cannot convert an object of type, it gives me an error. Convert type t, where t grid agent tuple. Oh wait, this is not an this is not a, I'm sorry, this is not an array, but it's a specifier for the grid agent, and we put this in curly braces. So if I do this, now I get a valid grid agent. What this agent now has, if I can quickly instantiate one, so I can do person, and if I call this, there is no method matching person. Why? Because it requires at least an int64 and a tuple of 2 integers, because that's what agents do. They have an ID and they require a position, in this case in a 2-dimensional grid, and that is the smallest possible agent we can have. It is agent number 1, and he's in position 1, 1. But that's not everything we want to store. We also want to kind of keep track of whether that person is healthy or not, and in this case we just track his state as the health, and let's give it an int64. The idea here is that we can, in this variable, we can basically say if that variable is 0, he is, or she or it is healthy, and 1 would be infected. And in the domain, we don't call it healthy, but we call it susceptible. So this agent can now, if I get a new agent, I can now tell it it's ID 1, it's in a position, and I can now tell it this is a susceptible agent. Oh, I have to first invalid redefinition of constant person. That's a thing that you might come across. The thing with structures such as person is that you cannot redefine them in a running Julia session. The problem with redefining the same name over and over again is that the rest of the code that has been relying on that person, that the way it was defined, could now in theory break, and that's the reason why you can redefine methods, because you can have additional methods, but you cannot redefine structures such as an agent in this case. And the reason, the reason I just explained, but the way to handle this is by closing the Julia console, opening it up again, and running all this again. And I'm basically just highlighting it and pressing Shift Enter, and it will take a moment. Person is, oh, that's interesting. For some reason I had a typo in here. I don't know when that happened, but it happened. And now I have this single susceptible person. Okay, we can have a person that can get infected, and obviously a person is not infected forever, so we should probably store like how many time steps has this person been ill, if he is ill, if he or she, I'll call it a him just because, no, let's call it a it. It, the person, it is ill, and we want to keep track of for how long he has been ill. Let's do int64, and that basically says how long has the agent been ill, and we'll keep it at 0 if that agent is healthy. So now obviously we can't update it, we have to reload Julia again. But I think this is the most simple version of how an agent could become healthy and ill. And what we now need to do is create an agent-based model from that. So typically what we would do is we would do agent-based model. And this gets a type of an agent. And let's put this in model equals. And this one will get a person, and it will get a space. And I think that's already enough. ABM is not defined because I have not loaded the rest in. So let's load the rest in. And as soon as we load in agents, we should have a standard ABM. So this model now is a standard agent-based model. It uses a grid space single with size 2020, a Chebyshev metric for neighborhood. It's not periodic. It uses the fastest scheduler, not the random one, but that's okay for now. We're going to ignore that, and it has 0 agents added to it. We can now define a person, and let's do that on position 1.1, and that person is healthy, and he has been healthy for, we don't keep track of how long they have been healthy, and I would call that person P. And this person is now a person on its own. It's not inside of the model. We have to add that agent. And the easiest way would be add agent, and we would do agent and model. And this will change our model. Oh, not agent. We want to add the person P to that model. And now in this model, if we call it, we see that the standard ABM now has 1 agent, or down here, 1 agent of type person. And the reason for that is that the add agent function that we called has an exclamation mark. And that means, warning, this function, when you call it, will change your variables. So the model variable that we supplied here was changed by the add agent. And in this case, actually, since we're using a grid space single, we can also do add agent single, which is a little bit more time efficient. And the agent can now no longer be inserted because we already have an agent with ID 1. We can quickly change this to 2, and now we can add the second, and now we have 2 agents of type person in this model, and that person, at the moment we insert it, we also get the new coordinates. This person is now in position 7 and 12. And yeah, these are basically the 2 agents that we have in our model right now. the behavior of the model is probably not the next thing that we want to do, but we would probably like to have some general properties of this model, because currently we just have person and space. But if you remember, we have had a properties variable, and let's do the properties, and that is a dictionary, and the dictionary typically has symbols, and they are assigned values, like the symbol is value 3. But the question is, what do we want? We should think about something like, if two agents meet, how likely is it that they will get infected? So we could have something like the, let's call it susceptibility. The susceptibility is a percentage of likelihood that one person will get infected if the other person was infected if they meet up. And we will basically say 30% chance for infection on meeting an infected person. And we can now give these properties to the model. Let's define the properties and let's redefine the model. We now have 0 persons in there, but we can now see down here that it has the property susceptibility, and this is now available as model.susceptibility, and we can now access this variable from the model as it's directly assigned to it, which is really helpful as soon as we get started with programming. So this is obviously just lots of code in line, and if you remember, it is good practice to have your model be generated from a function called initialize. The initialize function should have an end here, and the most simple way of doing this would basically just be this. And now once we call initialize, let's do it down here, initialize, this should generate a new model, and we can do it over and over again. It will always generate a new model. So here we could, instead of calling model, we would do initialize and call it like this. And let's remove this. We don't need this here. And now we have the smallest possible version of generating a model from a function. Obviously, this properties is only needed inside of this function. So let's move the properties in here. So now the initialize function will also, this properties variable is now no longer accessible to the global scope. So if I go properties here, it is now available because it's in memory and because I created it. But if I restart Julia and run all of this, we will have the model in the end. Sorry, I hope I'm not going too fast, but we will not have the properties because the properties variable is only defined inside of this initialize function. But that's the only place we need it, because in the future we will access it by going to the individual model properties and not by looking at the properties object directly. So we might want to change this susceptibility, so it makes sense to think about the initialize function as a function that has keyword arguments. And we can basically say, let's say susceptibility is a parameter that we want to change, and we put it as 0.3, and in here we replace it with the variable from the function. So what now happens, obviously this comment is no longer valid. If I replace the model function, I can now initialize it like this, and model.susceptibility is now not available. Why is that the case? Susceptibility, did I misspell it? Yes, I did. Susceptibility, that's how it should be written. Susceptibility, okay, that's the susceptibility, okay, that's better. So now if I do it like this, it is available. And I can change it by giving this here a parameter, susceptibility. I hope I'm putting this in right. And by doing this, I can now get a model with a susceptibility of 0.0, so with a much lower probability of infections. And the benefit of this is that we can now generate lots of models and evaluate them. We haven't seen how to evaluate them, but we have now a susceptibility in here that we can change from the initialize function. The other thing that we should probably think about is how long are people ill? So let's put a illness duration in here as well. And that should be a parameter as well. So let's do illness duration and let's, I don't know, pick 10. People are ill for 10 days. Illness duration. So if I redefine this function, I can still call it only with susceptibility and we'll retain the default 10 because it's still there. We can prove that it's there by going illness duration, it's still 10. But we could also at the same time just say, okay, let's give it a 5. And from this we can now have quickly a model with 5 days illness duration and a low susceptibility. So we can go from norovirus to something like COVID, which is probably more like, I don't know, 7, by just changing the parameters in the model. Obviously, at the moment, nothing's happening. We don't have a single person in our model, and we haven't visualized anything. We haven't seen anything. So we should think about how we get actual people inside of this model. And we should probably do this here. In this step, we have the model defined, and we saw we have this function called add agent single, and this will require an agent and a model. And if we do this multiple times, we can have, let's do it like this, 1.1.1. It is healthy and it hasn't been ill. So if I do this, we now get a model that has one person in it and on a random location. Obviously, we don't want to only have one person in it. We want to have multiple people in it. And maybe we should also, the space is now defined here globally, and I'm not really sure that's necessary. So let's take this space and put the space in here as well. So we'll define the space here, and I think it's a good idea to move the grid dimensions, so this value, also into the initialize functions. So let's put this is probably a thing we might be willing to investigate sooner. So let's say grid dimensions, dimensions, and this should be a tuple of 2020 if it's default, and here we can just remove this and say grid dimensions. And the benefit of moving this to the initialize function is that the initialize function, it works very well even if I don't put anything in here, because we have same defaults, namely the one that we put in here, and we can optimize this a little bit for readability. So let's put it like this, and then we can see all the individual parameters on a single line, and these are the default options for the initialize function. These are the model properties as defined in the method. Method is a terminology from object-oriented programming. So let's say function as defined in the function parameters. And well, now we only have one person. That's not what we want. We want to have multiple people in this grid. The question is, do we want the grid to be filled? So the grid dimensions now go from 1 to 2020. And in this case, let's call it total agents, because that's how people often call this. And I put in a number, maybe 400. Does 400 even work? We'll see. So we want 400 agents. So we need to define 400 agents. And these 400 agents, they all need to be added to the model. So what we do here is, by the way, I just saw we had an error in here, because if I initialize this and now have a look at model, now model is no longer the model, but it's the last person that was added. And the reason for that is whatever is in this function, the last line that has been executed, the return of this function is returned, the result of this function is returned as the result of the outer function. So we should probably do something like return model to make sure that this function actually returns a model with that person and not just that person. Okay, we want to go from all these persons, so we do an iterator for I in 1 to total agents. And we do something in here, namely we create this person and we add this person. The persons in here should all be healthy, and we can only have each ID once. So the easiest way to do this is by adding the ID as the iterator variable. And now we create a person with a different ID on position 1.1. It's healthy, and they have been healthy for as long as this is possible in here. And now they are added to the model. And if I do this, we should now have a standard agent-based model with 400 agents in them, occupying all the individual spaces. And all of them are healthy. So we should probably make one person ill. And how do we do that? There is a function that I think it's called getAgent. Get random agent, maybe? No. It's just random agent, random agent. Random agent, return a random agent from the model, and we can also define a condition and optimistic. Well, let's just do get me a random agent, and we'll call this person sick person. And we should make that person sick. So sick person dot health should be 1. And now we have this one sick person in our model. And we have now 400 agents, and one of them is sick. But we cannot see anything. It's all inside the memory. There's only, I mean, we can go model, and then by putting brackets in here, I can access the individual agents. So that fourth person is on space 711, and he's not ill. So we could, in theory, just try to go through all the different agents and see which one is ill. That doesn't make sense. We want to visualize this. So since the video was getting kind of long here, I'm quickly interrupting myself here from future me, and I will split this video, I think, in 3 files. The next thing we'll see is how I create a visualization for our agent-based model, and it would make sense to try to follow up to this point and then see if you understand what has been happening and if you can manipulate some of the functions that we've been using. And I'm already looking forward to seeing you in the next video.